Hi friends, welcome to our channel. Okay, today we are going to continue our topic atomic structure intermediate first year chemistry first chapter. Okay, last class we discussed about discovery of electron by J.J. Thomson, experiment of discharge tube. Now we are going to see another experiment of J.J. Thomson, which he calculated the charge to mass ratio of electron. See how he calculated. Let us discuss. See, this diagram is also a discharge tube, which is some different from the previous diagram you have seen in the first video. But this is also a discharge tube. But here there is one difference. We have taken the electric field and magnetic field. In the previous diagram, we have not taken it. Now see how he calculated the charge to mass ratio of electron. Okay, in 1897, British physicist J.J. Thomson measured the ratio of electric charge to mass of electron by using cathode ray tube, which is also called discharge tube, and applying electrical and magnetic field perpendicular to each other as well as path of electrons. In this discharge tube or cathode ray tube, he taken electric field and magnetic field, which is perpendicular to each other. The electric field and the magnetic field are perpendicular to each other, and they are perpendicular to the cathode ray particles, cathode rays also. So these are the cathode rays, these orange red color marks, and this is the blue color ones is the electric field, and the red color ones, orange ones is the magnetic field. Those two are perpendicular to each other, as well as those two are perpendicular to the cathode ray particles also. Now, in the presence of electrical or magnetic field, the cathode rays deviate rather than going in a straight path. We already discussed in the previous video that whenever there is no electric or magnetic field, the cathode ray particles travels in a straight line. But when we have taken any electric field or magnetic field, those cathode ray particles deviate. See how it deviates. When only electrical field is applied, the electrons deviate from their path and hit the cathode ray tube at point A. See, when let us assume that only this blue color one's electric field only is applied. What happens is whenever the cathode ray particles are comes, they deviate and they hit the cathode ray tube at this point A. They do not hit the cathode ray tube at point C or either point B. They only deviate and hit the cathode ray tube at point A. Now, similarly, when only magnetic field is applied, electron strikes the cathode ray tube at point B. When we have taken only this anode, this magnetic field, these cathode ray particles touch the fluorescent screen or cathode ray tube at point C. They don't touch the sorry here a typing mistake, not point B. They touch at point C. Whenever magnetic field only is applied, only we have taken this orange red bar, the cathode ray particles touch the fluorescent screen on point C. They do not touch the fluorescent screen at point A or point B. Now, how he calculated without balancing both? Is it possible without balancing both fields? How he calculated? He balanced both electrical and magnetic field. Without balancing, we cannot calculate the charge to mass ratio of electron. So, by carefully balancing the electrical and magnetic field strength, it is possible to bring back the electron to the path followed as in the absence of electrical or magnetic field, and they hit the screen at point B. Now, what happens is when he balances both electric field and magnetic field, when he balances at the same level the electric field and magnetic field, the cathode ray particles touch the fluorescent screen at point B. Likewise, when we have not taken any field, the cathode ray particles also touch at point B. When we balance both fields, the cathode ray particles also touch point B. Here, what happens is it is easy to calculate the charge to mass ratio. It is easy to calculate the mass of the cathode ray particles and the charge of the cathode ray particles and the ratio between both. Now let us see some more points. Okay. By carrying out accurate measurements on the amount of deflections absorbed by the electrons on the electric field strength or magnetic field strength, Thomson was able to determine the ratio of charge and mass. By amount of deflections or deviations shown by the cathode ray particles, by carrying accurate measurements, by measuring the deflection, accurate measurement of the deviations, he on the electrical field strength or magnetic field strength, Thomson was able to determine the ratio between charge and mass, which the ratio of charge and to mass ratio of electron is 1.758820 into 10 power 11 coulomb by kg. Okay. Now he observed some more points on the deviation of the cathode ray particles. Okay. Amount of deviation is directly proportional to the magnitude of the charge on the particle. Means if the charge of the particle is more, the amount of deviation also more. If the charge of the particle, cathode ray particle is less, the amount of deviation is also less. This is the main observation he observed. And also, the amount of deviation is inversely proportional to the size of the particles. Inversely proportional here. So, if the size of the particle is more, then the amount of deviation done by cathode ray particles is less. If the size of the particle is less, then the amount of deviation is more, he observed. And the amount of deviation is directly proportional to the strength of electrical or magnetic field. See, when we take an electrical field and when the electrical field strength is more, then the deviation produced by the cathode ray particles are more. Or else we take a magnetic field, when the magnetic field strength is more, then also amount of deviation produced by the cathode ray particles is more. Now, specific charge of cathode rays does not depend on the nature of gas. We all discussed in the discharge tube. It does not depend on the nature of gas taken or the metal electrons also. Okay. Now, this is the charge to mass ratio of electron. The main thing here is the ratio 1.758820 into 10 power 11 coulomb by kg. Very simple. Only observations we have to know. When electrical field is taken, it deviates at a point A. When magnetic field is taken, it deviates at point C. When the both fields are arranged balanced well, it touches the fluorescence skill at point B. Okay, this is the cathode and this is the anode. This is the voltage. We know the conditions: high voltage and low pressure. And this is about the charge to mass ratio of electron. Okay. Now let us discuss another scientist experiment who determined the charge of the electron. So, Millikan's oil drop experiment. He determined the charge of the electron. R.A. Millikan devised a method known as oil device experiment to determine the charge of the electrons. Okay. Okay. Now, this is the apparatus we have taken for Millikan's oil drop experiment. We have seen atomizer, oil droplet, charged oil droplet, charged metal plate. Here we have taken two metal plates, which is anode, which is cathode, and which is anode. So here the charged metal plate is a positive and here negative. And here using microscope to view the oil droplets, Millikan taken. And here the ionizing radiation means through this ionizing radiation we have sent X-rays to the oil device. Okay. Now this is the voltage. You know that. Now what is the method? Let us see. Now what are the observations he did after the experiment? Let us see. Millikan calculated the charge of the particles, which are some slowed down, going down, some stopped in the middle, and some are moving up. Now let us see the diagram. Now what happens here is, through pressing the atomizer, so here the atomizer, through pressing the atomizer, While we press atomizer, some oil droplets are pushed into the oil device. Here we have seen some oil or sprinkled to the oil device. Now the sprinkled oil droplets, they move through a small hole on the anode, the positive plate. Okay, the positive plate. Through the small hole, the oil droplets are bent down to the negative plate. What happens? The gravity pulls these oil droplets into it. We know that the gravity pulls the oil droplets through the negative plate. Now, while we have connected to the voltage here, what happens is through the ionizing radiation, we have sent some X-rays, right? The X-rays, they collide with the oil particles. While collide with oil particles, the oil particles become slowed down. Okay. So while the X-rays collide with the oil particles become slowed down. So why the oil particles become slowed down means the charge in X-rays was acquired by oil particles. The oil particles acquired charge and they become slowed down. Some particles move upside. The acquired charge particles, they acquired negative charge through the X-rays. This negative charge attract towards the positive plate, right? Means unlike charges attract each other. These unlike charges attract each other, and some oil particles move upside, some are slowed down, and some particles they stop at the middle. So this Millikan, he calibrates the charge of the particles. The three types of particles he calibrated the charge, and he observed that all the charges are integral multiples. All the charges are integral multiples, which is equal to Q equal to Ne. Here E is what? E is the charge of the electron, which is 1.6 into 10 power minus 19 coulombs. And Q is the charge we know, and N is the integral multiples, means integers. Either we take 1, either we take 2, 3, or so on, so on. Now, let us see a small demonstration. So, the voltage, they become charged and they move from a positive plate to a negative plate, and through this hole, the X-rays are comes down and collide with those. Okay, through this hole, we sent X-rays and they acquire charge and they slow down. They slow down, and when they slow down, and we can control those particles. We can control gravity through by connecting the battery, which is voltage. So when we increase the voltage, what happens is they slow down, and when we decrease it to zero, what happens? They move randomly. When we increase the voltage, they will slow down again. So we can control the gravity here. Through this, the Millikan calculated the charge of the three type of particles. So he observed charges are the integral multiples. And he found the charge on the electron to be 1.6 into 10 power minus 19 coulombs. The present accepted value we are using is 1.6022 into 10 power minus 19 coulombs. And he also determined the mass of electron by combining these results with Thomson's value. We already discussed E by M value, which is 1.758820 into 10 power 11 coulomb per kg. The coulomb is here charge and kg is mass, SI unit. Okay, or we can write coulomb kg inverse. So here M equal to the value of E by M comes to down, which is division, and M values goes to the RHS side. Now by calculating this division, we can get 9.1094 into 10 power minus 31 kg, the mass of the electron. Okay, now we are using 9.11 into 10 to the power of minus 31 kg. The accurate value is 9.1094 into 10 to the power of minus 31 kg. Through this, Thomson determined E by m value, but Millikan's he calculated the charge as well as the mass of the electron by Millikan's oil drop experiment. Okay, this is today's class. Hope you understand well. It's some confusing, but when we see if you see the video full and if you see again, then you will definitely understand it. It's a very easy topic. Just we can understand. It is very easy. Okay. Now in the next class we will discuss about discovery of again two subatomic particles, proton and neutron. Okay. Thanks for watching and hope you like the video and please subscribe and share the video. Thanks for watching.